We have already discussed how to solve for the local and average nusselt numbers for flows over flat plates. Now let us focus our attention in analyzing convection heat transfer due to the flow of fluids over cylinders and spheres. Let us start our discussion with determining the local nusselt number. Here is a snapshot of a 3D simulation of the fluid flow over a cylinder. Let's say that we want to determine the nusselt number only at this point in the fluid flow, represented by point P. Then what we need to do first is to measure the angle between the line connecting this point to the center of the cylinder and the line connecting the center of the cylinder to the stagnation point S. The stagnation point refers to the point of the maximum pressure in a fluid flow. The fluid has the highest pressure at this point because the kinetic energy at this point becomes zero and is therefore converted entirely to pressure energy. Once we know the value of the angle theta, we can now determine the value of the local nusselt number at that point, which is denoted by nu sub theta. The local nusselt number is dependent on the angle of the point from the stagnation point, the average Reynolds number, and the Prandtl number. Take note that for flows over cylinders, we can determine the value of the local nusselt number using this graph. Characterizing fluid flow over curved surfaces such as cylinders and spheres is quite difficult due to the presence of a low pressure region at the downstream side of the surface. This is represented by the light blue region in the flow simulation snapshot shown here, and it is called the wake region. Therefore, due to this flow complexity, we have become more interested in knowing the average Reynolds number instead of the local Reynolds number for flows over these curved surfaces. The average Reynolds number is still computed using this formula. The only thing that will change is the characteristic length that we will use in the formula. For flows over cylinders and spheres, the characteristic length L sub c corresponds to the external diameter d. As a final note, the critical Reynolds number for this type of external flow is 2 times 10 to the 5th. Now let's present the correlations for computing the nusselt numbers for flows over these curved surfaces. Let's start with the correlation for computing the average nusselt number for fluid flow over a cylinder that is kept at a constant surface temperature. For this, we use the Churchill and Bernstein correlation, and it is represented by this formula. Take note that this correlation is only valid if the product of the Reynolds number and the Prandtl number is greater than 0.2. Now obviously, this correlation involves parameters whose values are dependent on temperature. So on which temperature value are we going to base the value of these parameters? For flows over cylinders, remember that the Prandtl number, the fluid thermal conductivity, and the parameters to compute for the Reynolds number should all be based on the film temperature T sub F, which is just the average of the surface temperature and the free stream temperature. Now let us present the correlation for finding the average nusselt number for flows over a sphere that has a constant surface temperature. For this purpose, we use the Whittaker correlation, which is represented by this formula. Take note that this correlation is applicable only over the following ranges of values for the Reynolds number, Prandtl number, and the ratio of the free stream viscosity and the fluid viscosity at the surface of the sphere. Finally, when using this correlation, the values of the Reynolds number, Prandtl number, the fluid thermal conductivity, and the free stream fluid viscosity all depend on the free stream temperature T sub infinity. On the other hand, mu sub s corresponds to the viscosity of the fluid in direct contact with the surface. Therefore, its value is based on the surface temperature T sub s.